We said implicit differentiation is particularly helpful when we're working with relations which are not functions. So here I have the graph of a relation which is not a function. I can draw in a vertical line and show, okay, it intersects here, and it intersects here. This is most definitely not a function. So it's not a function. And when we're working with things that are not functions, we can have some odd things happen, some weird stuff. So let's just go through these questions and kind of see what I'm talking about here. First says, how many tangent lines does the graph have when x equals 6? So if I go to x equals 6 right here, well, there's only 1 point. I'm going to have one tangent line. I can actually just sketch that in. I've got a vertical tangent line, but it's a tangent line. So how many tangent lines does the graph have when x equals 6? Well, I've got 1 there. What about 5? How many tangent lines does the graph have when x equals 5? So if I look at 5, I end up with kind of a different problem here because I've got a point right here, and I've got a point right here. I don't really know which one to take, so I guess I have to take them both. If I were to sketch in those tangent lines, I've got a tangent line right here, and I've got a tangent line up here. I actually have 2 tangent lines. So when x equals 5, I actually have 2 different tangent lines. When x is equal to 2, let's erase some of this just so that we don't get confused by it. When x is equal to 2, so at this x value right here, how many tangent lines do I have? Well, I have 1, 2, 3 points when x is equal to 2. So that means I'm going to have 1, 2, 3 different tangent lines. So when x equals 2, I actually have 3 different tangent lines there. When x is equal to 0, this is even going to be worse. I've got 1, 2. This one's tricky because I have 1 point there, but I'm going to have 2 different tangent lines. And 3 right here. I have a tangent line right here. Notice that it sort of passes through this point. You can almost think about it as passing through that point 2 different times. I've got 2 different tangent lines. I've got this one right here, and then I've got this one right here. Oh, and let's not forget this point right here. It's going to give me a different tangent line. Actually, I have 4 different tangent lines when x is equal to 0. So this is really odd because I have, depending on what x value I'm talking about, I might have 1 tangent line, I might have 2 tangent lines, I might have 3 tangent lines, I might have 4 tangent lines. We're used to having 1 tangent line always because we've only been working with functions. But now we have this weird scenario where depending on what x value you're talking about and depending on what your function looks like at that particular x value, you may have more than 1 tangent line. So again, just to emphasize why we care so much about implicit differentiation is we can find the slope of the tangent line, right? We can find the derivative of these relations which are not functions. So we can do our classic calculus examples. We can find the equation of the tangent line for graphs which are not functions, for relations that are not functions. But I end up with this weird scenario where if I say find the equation of the tangent line, you might say, which one? I've got 1, 2, 3, 4 of them. So here's an example. I have the graph x squared plus y squared equals 25. I want to find y prime and the equation of the tangent line when x is equal to 3. So if you were to actually graph this function, what you would see is you would see a circle centered at 0, 0 with a radius of 5. 2, 3, 4, 5. 1, 2, 3, 4, 5. You would see something that looks like this. It's obviously not a perfect circle, but when x is equal to 3, let's look at that. 1, 2, 3 right here at this x value. I've got a point right here, which gives me a tangent line right there. And then I've got another point down here as well. I'm going to end up with a separate tangent line right there. So I actually have a typo in this problem then. It should say find the equations of the tangent lines at x equals 3. I might have more than one here. So let's just get right to it. And actually, before I jump in, we're working with x squared plus y squared equals 25. You might say, well, implicit differentiation is great at all, but I don't really want to do it. I just like explicit differentiation. I'm going to do it the old way. And I'm going to show you why maybe that is, why it's problematic here, why perhaps it's more challenging. Explicit differentiation says we got to solve for y first. So y squared equals 25 minus x squared. But when I take the square root, I'll have y equals plus or minus square root of 25 minus x squared. So I really have actually two different functions. I have y equals positive square root 25 minus x squared, and y equals negative square root 25 minus x squared. So if I want to find y prime, I actually need to find the derivative of two separate functions. Which, okay, even if you're really good with your derivative rules, you could use some of those derivative rules to speed up that process a great deal. But I'd still have to use the chain rule right here. I'd still have to use the chain rule right here. I would need to rewrite this expression. It's not going to be particularly enjoyable. And then at the end of all this, you're going to run into problems with deciding what derivative to plug in your x value to. Do I plug it into the derivative of this function, or do I plug it into the derivative of this function? So this is probably not a great way to do the problem. So here, this is why implicit differentiation is really gonna help us out. Because if I'm working with x squared plus y squared equals 25, my first step is, okay, let's just take the derivative. Take the derivative of each side with respect to x. So the derivative of x squared, that term just has an x. That's just going to be 2x like it normally is. Derivative of y squared, that'll be 2y, but I need to remember that y is a function of x. I need to use the chain rule, so I need to multiply by y prime. Derivative of 25 on the right-hand side, that's a constant, so derivative of 25 is 0. And now I just need to solve for y prime. Well, this shouldn't be too bad. I've got 2y y prime equals negative 2x. So y prime equals negative 2x over 2y, or simply negative x over y. That was sure a lot easier than, solving for y, ending up with two different functions, having to take the derivative of two different functions, ending up with two different derivatives using two different chains. Like, this was so nice. I did this in 4 steps. So this is why implicit differentiation can be so helpful. And there may even be problems, we'll see in I believe in the next example, there may even be problems where you can't even solve for y. There's just no way to do it. Implicit differentiation is the only way to do that problem. So okay, we've got our y prime. This is equal to y prime. Now we want the equations of the tangent lines when x is equal to 3. So let's think about this for a minute. Whenever I write the equation of the tangent line, right, I need 3 things. I need an x value, which is given to me, that's 3. I need a y value, I don't have that. And I need a slope, I don't have that either. Now, if you want to find the slope, right, that's the same as the derivative, but in this case, the derivative depends on both x and y, which means I need to find my y value first here. That just means I need to go and find my y value before I can find the slope of the tangent line. And to find the y value, I'm going back to that original equation. I'm going back to x squared plus y squared equals 25. So if I work with x squared plus y squared equals 25, x, that's 3 squared plus y squared is equal to 25. So I have 9 plus y squared equals 25. So that means that y squared is equal to 16. Y is plus or minus 4. So here's where I have this interesting case where I actually have two different y values. We said that was probably going to be the case. We said earlier if you were to sketch this, you would end up with the graph of a circle and that we would have a tangent line, say right here and right here. So I actually have two different y values. I've got positive 4 and I've got negative 4. Which means I'm going to end up with two different slopes. So perhaps I should rearrange this because I think the way that I've written this is perhaps a little bit confusing. So let's do this. I'm going to have two different points essentially. I'm going to have a point at 3, 4. And then I'm going to have another point at 3, negative 4. And because I have these two different points, I'm going to end up with two different tangent lines. So let's find the equations of these tangent lines. I've got the point for each one of these. I just need to find the slope. So let's work with 3, 4 first. I'm going to take my x value of 3, my y value of 4. We're going to plug those into our y prime equation because that tells us the slope of the tangent line. Y prime equals negative x, that's negative 3 over y is 4. Well, that's my slope. I can't really simplify that much more. I guess you could give a decimal if you really wanted to, but I'll leave that as negative 3 over 4. And at this point, for the left-hand side, for this point, I have everything I need because I've got my x value, I've got my y value, I've got my slope. I can write the equation of my line. So y minus my y coordinate is 4 equals m, that's negative 3/4, times x minus my x coordinate of 3. And then you would take that equation and solve it for y, and I'll leave that up to you. At this point, we've seen that so many times, I think we're probably pretty comfortable with that by now. Over here, for 3, negative 4, I'm going to follow mostly the same procedure. So I need to find the slope because I have my x value, I have my y value. The only thing that's missing is the slope. So y prime is equal to negative x, that's negative 3, over y is negative 4, which I know is the same as a positive 3 over 4. This is the slope of my tangent line. So again, I have everything I need now for this point. I have my x value, I have my y value, I have my slope. I should be good to go. Y minus my y coordinate is negative 4, so maybe we'll just write that as y plus 4, equals m, that's 3/4, times x minus my x coordinate is 3. And then again, you would take this and you would solve it for y, but I will leave that up to you. So be very careful with these types of functions because you may end up, if you end up with more than one y value, that means you're going to have more than one tangent line. So we'll look at one more example like this in the next video just so that we can feel a little bit more comfortable working with multiple tangent lines.